So, in order to make a buffer solution, you need to choose carefully what components you're putting inside because you need to choose what pH is suitable to the biological system you're trying to maintain. For example, if you have an enzyme that works best naturally at pH 8, then you're going to want a buffer solution whose natural pH is around 8. Then, the buffer solution will resist pH change in both directions. So you'll have something in there which will take up extra H+, which is added, and you'll have something which will take up extra OH-, which is added. So as such, the most common one would be a salt, which gives up a conjugate base of a weak acid and a weak acid itself. So if you're confused by that, let me explain, okay? Let's start with the salt. So let's say, for example, we have sodium ethanoate. Now, sodium ethanoate is a salt that completely dissociates, dissolves in solution because it's a group 1 metal ion salt. You'll have Na plus ions, which do not affect the pH in any way, that's quite important. And you'll have ethanoate ions, CH3, COO minus. Now, when you add H plus extra to the solution, then that H plus will bond with that ethanoate ion, because that ethanoate ion is the conjugate base of a weak acid, ethanoic acid. So ethanoic acid, as a weak acid, therefore has a strong conjugate base. By adding lots of the conjugate base in the form of a salt, say sodium ethanoate, then whenever you add H+, that base will immediately take that H+, and the pH will stay the same. Now, on the other hand, if you want to resist OH- going in and taking up all of the H+, you actually want to use a weak acid like ethanoic acid. Because ethanoic acid only gives up a few H+ ions, that means you don't greatly affect the pH of your buffer to begin with. It's much easier to control the pH of a buffer with a weak acid than a strong acid. So if you have a weak acid and you want a pH of, say, 6, you might put 0.1 molar of the weak acid. If you want a pH of 5, you might put 0.6 molar of the weak acid. It's relatively easy to control the pH with a weak acid. Whereas with a strong acid that completely dissociates, it's very, very sensitive. The pH will change too quickly with a strong acid than with a weak acid. So we tend to use a weak acid in our buffer. So we have our ethanoic acid. Let's say its pKa, its Ka off the top of my head is 1 times 10 to the minus 4, which means 1 in every 10,000 molecules will dissociate into H+ ions. You then add some OH- in there. Now what will happen is the OH- will take up all the H+, which is currently there, but then because of the equilibrium that exists with weak acids, some of the dissociated ethanoic acid will then dissociate again to restore the original amount of H+ in the solution. So you can think of our weak acid, our ethanoic acid, as like a supply of H+ ions, and that supply doesn't get released or used up until you add base in there. So you have a weak acid. 9,999 molecules do not give off any H+, and some of it does give off H+. Now you've added that in the first place because you want the pH to be at a certain amount, so you might add a lot of the weak acid for a high concentration of weak acid, or not a lot for a low concentration of weak acid. Then you add some base, all of the H+, which is there, gets grabbed, but because of the equilibrium you've lowered the amount of H+, so therefore the system wants to increase the amount of H+, causing your ethanoic acid to dissociate more. And that is the buffering effect. That is reducing or making sure the amount of H+ doesn't change as much as possible. As such, the pH stays the same and maybe your enzyme does not break.